All right, here we go, guys. Welcome back. Structures 2. We're going to start talking about columns here. So this is the format I'm going to do. Okay, I'm going to try to post a lecture by the time we usually have class, right, on Monday, Wednesday, and Friday at time to typically meet 2 o'clock. By then, there should be a lecture for the day. I might try to pre-record some of the lectures as we're stuck at home and locked. I'm currently locked in my office, the door shut, and have no interaction with anybody outside of my roommates. But obviously those are my kids. But so I have a little bit of time on my hands, so I might try to pre-record some lectures and post them online. The other thing that I would like to do is have a little bit of FaceTime with you guys, right? And so maybe a couple days a week. I haven't quite determined what that schedule would be. Maybe during our regular class time, I could be available for any questions and things like that you have regarding the class and the university in general. So there's a way I could do that via WebEx. I could just open up a room and then send you guys the link, and you guys can log on, and we could have a little interaction if you'd like, right? Or we can work through some problems or something like that. So, or go over homework issues and things of that nature. So that's what we're planning on doing. Jaden is currently breaking all of your guys' columns, and he's taking a video of himself doing so, and he hopes to post that online sometime today, which is very timely because that's what we're talking about today. It's columns, right? Exams, I think we're just going to stick with the regular exam style where I will post the exam online, give you guys 4 hours basically to do it, and then you can upload your solutions to Gradescope, and then I will grade them from there. I toyed around with the idea of just making it like short answer, true, false, fill in the blank type of problems, but I think that it's important to see that you know how to go through the whole process of a design, right? But stay tuned on that. I'm still kind of working out some of the kinks. I might break it up into a couple shorter exams instead of one long exam, but I'm still working out those kinks. But we are due for an exam pretty soon, right? And so sometime in the next week or so, I'd like to do that. The next exam would be on columns and continuous members and slabs, right? And so, and then that sets us up for steel design. So today, it will probably be our last lecture on concrete. We should be able to get through this. If not today, the next lecture, we'll get all the way through concrete. And then after that, we'll start steel. So hopefully you guys have ordered your steel manuals, and we could proceed from that. So again, if you have any questions or whatever, reach out to me. I'm here. I have time. I can answer questions and things of that nature. So so this is what I'm going to do. I'm just going to record this screen, right? This is usually what you see up on the board. You can't see my face. You'll see my face. Excuse me. Let's see here. Can you? Let's see here. Hey, what you guys doing? Okay. Sitting in my office, hanging out, all by myself. So, by the way, this is way stranger for me than it is for you, right? It's a little strange for you to be watching this video on the lecture and stuff like that, but I'm sitting in my office completely by myself, talking as if you're sitting right in front of me. So, it's a little strange experience, but I have done it before. It seems to work all right, right? If anything, it might be a little bit better for you because then you can fast forward me, you can pause me, you can rewind, whatever you need to do. So, like I said, I think that this will work out pretty well. I will post some skeleton notes online, but then after I give the lecture, I'll also post the completed notes as well. So you'll have both of those things to access as well. So hopefully you guys are staying safe, staying entertained, right? And hopefully nobody has fallen ill and whatnot. It's a little scary times, but it should be. I think everything's going to be okay, right? It's very interesting times, and maybe I mentioned this before, right? This is going to be this is a big deal, right? I think you'll always remember this time in your life as being scary or whatever, but everybody's just kind of hiding out, slowing down, and to be honest, just enjoying life a little bit more once everything slows down. I've gotten to know my roommates a lot better lately, right? My kids and my family, we've been spending quite a bit of time with each other, and it's actually been quite pleasant. So, anyways, we will, I guess let's get started. That's enough of that. So we were talking columns, right? This is actually something I know a lot about, right? This is what my dissertation was on. And so what we did is just a quick review of where we stand in this regard, right? We were looking at short columns, concentrically loaded short columns to what we're looking at. So they have to be a certain height to width ratio. Otherwise, they fall under a different category, like under a pedestal design as opposed to a column design, right? And so we kind of defined what that was. We talked about this idea of rectangular tied columns versus spiral reinforced columns, right? These guys are better. As you're going to see in those videos, hopefully with the Jaden post today, you'll see that the spiral columns behave better, right? I mean, you can see this thing is just like right, it goes around like that, and then they kind of splice. You can see that there's a little one here, and then they overlap a little bit there. And they're just not as effective, right? I mean, just your intuition should say this guy's, spiraling around, and it's one continuous bar the whole time, and it's just kind of holding things together. And it does a lot better than these ties, right? Typically, you find ties in rectangular columns, and in circles, you'll find the spiral columns. And the purpose of these ties and spirals are to confine the core, right? So this is the core in here, right? That's in here. And when you squish the concrete, it wants to squish out on the side. Poisson's effect makes it want to squish out on the side, and then which causes tensile stresses, which will then cause failures. And to resist that, you put in these ties going across, and it just kind of holds the middle together. It wants to bulge out, right? It wants to go like this, right? And then you have these ties that are holding it together, or you have these spirals. There's one continuous member like this that are holding all of those ties together, or holding all the reinforcement together and holding that core together. By holding that core together, you're going to get a higher capacity. Okay. The other thing it does is it prevents these bars right here from buckling. Those bars want to buckle out under compression, but if you have the ties there, it keeps them from buckling out. We also went on to talk about these composite columns. You could put an I-beam inside of a spiral, inside of regular reinforced concrete like this, and that works pretty well, right? But what happens with these things is you can have the concrete kind of spall off on the sides here, right? Right, you can have something like that, and then same thing with this, right? It's just like, let's encase a steel beam in concrete, right? And they use that on occasions. This is more popular though, right? Is to have the steel pipe on the outside, and then you fill the pipe with concrete. Works beautifully together. The concrete prevents the bar or the pipe from buckling on the outside, and then likewise, when this thing wants to go through Poisson's effect and wants to bulge out on the sides, right, and has this external pressure like this, you have this pipe in there that kind of holds it all together. Kind of holds everything together, and you get beautiful response out of this. And we have a research project with MDT right now, specifically looking at connections between steel pipe piles and concrete-filled steel tubes and concrete pile caps. As we have the big research project, we're going to be testing a large-scale specimen that looks like this, and we're going to push on the top of it like that until we get failure. And so that will hopefully be going down this summer, assuming we're ever let out of our houses and offices and stuff like that. But if not, it'll start next fall. So anyways, that's another thing. We're not really going to talk about the design of these guys. I just wanted to let you know that these things exist. We're going to be talking about the design of rectangular tied columns and spiral reinforced columns. And so that's as far as we made it on whatever day it was, that Wednesday before spring break. Okay. And so, the next talk, I guess, we'll just keep going with these notes right here. Right. And so, this is what that lab was designed to kind of show you, right? When you apply a load, so this is exactly what we're going to do with our our lab, you made a couple different versions of columns. When you apply an axial load, right, this is just like testing our cylinders, right? You apply a load until this thing squishes, right? And so if you monitor how much force you applied and then how much it displaces, right, and you plotted it on a graph, this is what it looked like. And this is very similar to beams as well. If you had just regular reinforced concrete, just regular concrete without any reinforcement would go like this. It would go, it hits about its ultimate capacity, and it ruptures, okay, or it breaks, right? That's just like if you're testing a cylinder, right? So your column that you made in lab should fail like that, in a very brittle fashion, no warning whatsoever, and then it loses its capacity. If you include ties in there where you can find the core, right? I'm going to draw it in green here. It would look like this guy. Right, that's this graph right here, right? And so you get a little bit more ductility. And where do you get the extra ductility? Well, you get these ties, right, are kind of holding the core together. If they're spaced too far apart, right, then they're not going to confine this core very well, right? But they will confine it in some capacity, right? And so that extra, ductility that you get out of it, right, it goes like that, right? It kind of goes up and around, and you get a little bit extra ductility because you've add those ties. But if you include spirals, right? These spirals right here, kind of you can see them kind of working their way around like this on the way up there, right? That really is effective at confining the core. It's one solid bar. You don't have any lap splices, and then you get this behavior right here. Right? You get lots of deflection, lots of warning before failure, and so as it would imply, you should get rewarded for that. You have a very ductile failure, and so you should get an extra reward for doing that, and you do. In the phi factors, you get a little boost because you have some extra ductility there, right? And so our test data typically in columns works out pretty well, right? Not perfect, but pretty good. Right, and especially the spiral one. The spiral one, you can see that it actually behaves like this. You get maybe not as ductile as is shown in that diagram, but way more ductile than the tide, the one without reinforcement, and the one without with just very few ties, just a tie at the top and the bottom. It definitely behaves better than that, and so you get this extra ductility for having that. The other thing I should mention is labs. I haven't quite decided what we're going to do with our lab reports. We'll probably keep going. We'll do one more lab report. I'm going to give you feedback from this lab report, and we'll do one more lab report on the beam designs, and I'll give you some examples of that, and we'll talk about that at a later time. And so, yeah, like I said, we'll do one more lab write-up. You guys get to collaborate remotely with each other. So anyways, we keep going here. Mechanics of concentrically loaded short columns. So how do these things behave, right? We haven't talked about calculating the capacity of these things yet. We just talked about the different types of behavior at this point, okay? And so how do these things behave? And in particular, we're only going to look at one type of column. We're going to look at concentrically loaded, right? So this means is we get no moment. Okay, no external moment on it, right? Concentric means you loaded this thing up perfectly. So in this guy right here, if that thing's lined up right in the middle, then that's a concentrically loaded column, right? If it was off center, right, that would be an eccentrically loaded column, right? We're not going to do eccentrically loaded columns because that's going to have bending and axial load on it at the same time, and so we're just going to do concentrically loaded short columns. And then in this, the short columns here, right? I was almost asking you guys a question. Like, so why do you think these things are called short columns? Why are these things called short columns? Well, it's funny that you asked that. Thank you for asking that question right there. The reason we're only looking at short columns is that we don't have to deal with buckling, right? No buckling. Right? As your column gets longer, right, that becomes a failure mechanism. When we go to steel design, steel, it is that is one of the failure mechanisms that we're going to have is buckling, right? You have very thin flanges and thin web. Steel's really strong, and so since steel is really strong, right, 60 KSI is at a 4 KSI that concrete has. 60 KSI is its ultimate capacity. 60 KSI right, you get to make your members smaller. If you make your members smaller, they become more susceptible to buckling and stability issues, right? But in columns, they're usually big and fat and massive, and so we don't really have to worry about buckling. Okay, there is obviously, if you have a really long column, you do have to design it, but that's beyond the scope of what we're going to teach you, okay, or what I'm going to teach you in class here. So concentrically loaded, we have no moment. At short columns, we're not going to consider buckling as being one of the failure mechanisms. Okay, so to kind of come up with this the equation for calculating the capacity is very similar very similar to what we did for beams, right? You start out with strains, right? We start out with strains, we then go to stresses, strains, then stresses, and then look at forces, okay? And then from that, we get, we're going to derive an equation. So the very first thing is when we apply an axial load, right? So this right here is the side view, or sorry, this is the cross-sectional view. So if you're looking down on it like that, and then this is looking at this thing from the side. So I guess it maybe be looking at it this way, right? Because I drew it a little bit narrower. So we're applying a load down right here, okay, and then we're looking at it this way, right? And so when we do that, right, ultimately how we're going to say that this concrete fails is we're going to say that it reaches a strain, a compression strain of 0.003, right? And if you may remember that from beams, okay, that we have a strain of 0.003. At that point, the concrete crushes, right? When we tested all of our beams, right, that was a failure mechanism for the over-reinforced and the ductile failure, the under-reinforced or the ductile failure that we had, or normal beam rather. It failed when the concrete reached a strain of 0.003 and crushed up at the top. And so we're going to assume that the concrete crushes at a strain of 0.003, okay? If we want the ultimate capacity, right? If we want the ultimate capacity, that's what's going to govern it, right? As soon as that concrete crushes, you're not going to be able to carry that capacity anymore. And then the other thing that's different about columns versus beams is that guy is not, right? When we did beams, we had compression on one side and tension on the other side, right? That's for axial load and bending. But then for these guys, it's just a uniform compression strain, right? Because there is no moment on this thing. We just apply the load. Now, if we then come over here and then look at these stresses are going to be doing this. All right, we'll show down being the compression. So each steel member is going to have an FS, and they should all be about the same length here because they're all concentrically loaded. They're all under the same stresses here. I'm going to move this a little bit. Okay, and then so you have each one of those things. Oh, I'm going to move those to it. Drew those in the wrong spot. How easy it is for me to do this. It's hard for you to do it. I apologize for that. But it's going to have the concrete. Let me make this a different color. The concrete's going to have a uniform stress on it like this. Right, and this right here is going to be 0.85 F prime C. That's what that stress is. And then each one of these guys, we're going to call FS, right? We can even call that, we'll call that FS3, FS2, and FS1. Right? They all will undergo the same amount of stress. Okay? And then once you have those stresses, we come over to the forces, and then those forces, you're going to have a resultant force. You're going to have the concrete resultant force, right? And then you're going to have, maybe I'll stick to my color scheme here. I'm going to have this guy right here, C sub C, concrete compression force, and then you're going to have one at each location for, I'm going to have a force here, a force here, and a force here. Again, those should all be about the same length. Let me redraw those. You'd think with this grid underneath here, I'd be able to make them all the same length. Just not paying close enough attention. I did it. Mostly. Okay. And so you're going to have CS1